Finally, we talked about the flashless forging, right? That also we also forging equipment, what we told the forging equipment we covered, but before that also we made it coin. Okay, so I give one example of how the coins actually we are manufacturing, whether the coin blanks initially we are manufacturing, that minting, that is other part. So how the coin blanks actually, that is important when we are making about the mechanical working, right? So today we will cover about the forging defect. Okay, so these also small time. Sometimes I'm sharing small information to you, but when typically we'll talk about the forging defects. So if you see the schematic diagram here, so this is forging defects. First one is the cracking or the flash. Okay, if you remember when we are talking about the flashless and when somewhere we are getting the flash, right? So here also cracking at the flash. Whenever we are talking or whenever you are removing the flash, near to the flash also you are making or you are finding some cracks there. And second one we have the pole shot or the fold. And third one, we have the internal cracking due to the secondary tensile stresses. Okay, so that's why all the parameters, because whenever somebody is telling or maybe customer they are telling, we have to make the defect-free material. Okay, if you have some defect, for example, I will give one example. One time I visited one ceramic company abroad in Turkey, actually. So that ceramic company, well, even I have never seen. Maybe somewhere we are looking here the how the small shops they are preparing some ceramic, but I visited a big ceramic company. In that company, it is good that they have a different segment or a different area. For example, somewhere manufacturing, somewhere this is testing, somewhere where it is going to the store, or somewhere it is keeping. Then they have some test. Like for example, they have. The visual test that they have, if you have very small cracks, then it is going to the NDT, non-destructive testing, and somewhere they are going for the tensile testing or the mechanical testing. Okay, so when they are finding some cracks or maybe some has some mistakes, then it will go to the other side or maybe other segment. And from that segment, somewhere if they can make it repair, then again it will go to the another segment, not to the original where they are sending to the customer. That's again it will go to the another zone, and which is totally damaged, then again it will go for the recycling. So you have to do. And if it is going to a perfect, if you are selling in a perfect way, then your whatever the cost or whatever the price you have, you can make it in a proper way. But if it is going to the little lower quality, then probably your cost will decrease. So that one also you have to take care, right? So here I mentioned surface cracking can occur as a result of excessive working of the surface. So two things we have to remember, three things we have to remember. One is what are the types of defect we have, and second is what are the cause and how it is finding or how it is creating. That one also you have to remember. And third thing, how to diminish or how to remove that one. So three things as a technical person we have to understand. So the surface cracking can occur as a result of excessive working of the surface at too low a temperature or as a result of hot shortness. So sometimes if you will see, whenever you have you are finding some crack, why? Because if there is a temperature gradient or maybe the difference of temperature, then you are finding some cracks. Okay, and one more thing also, we'll talk about the hot surface actually when we will talk about the sheet metal forming, maybe in module 5. We'll talk about. So why you are getting in hot surface? Because whenever you are doing some mechanical work, so you are finding the material and not uniform everywhere. Somewhere it is ductile, somewhere it is brittleness. Okay, so the moment you have changing in temperature or you are increasing temperature, you are finding somewhere the brittleness of the metal. So then they are finding some hot surface. A high sulfur concentration in the furnace atmosphere can produce hot surface in steel and nickel. You cannot say that for all the metal. Again, I'm repeating, you cannot tell that when sulfur concentration or sulfur content is high in all the material, because in case of steel and nickel, probably you are finding the sulfur concentration. So that therefore you have to think about the composition of the material. If you have the composition material, because all the material has a different or unique property, so that also you have to find out. And the cracking at the flash is closed die forging is another surface type. Okay, if you have the flash here near to the flash, if you have some cracks there, because you have to remove this flash, right? And if you have some cracks there, and probably the crack whenever you will cut it, maybe this crack can propagate inside. And the moment it will propagate inside, again you have some, you will face some damage there. Since the crack generally penetrates into the body of the forging when the flash is still on. So that means if it will penetrate inside to your product or to the inside, then again you will find some difficulty there. And this type of cracking is more prevalent the thinner the flash is in relation to the original thickness. So that means it can also connect to the, you cannot tell that everywhere because you have to find out the cause. So whether the flash, whether this is very thin or thick, also that depends upon the, like, how much crack you are creating there. That depends upon the thickness of the flash, whether this is thin or thick, that depends. And the flash cracking can be avoided by increasing the flash thickness or by relocating the flash to a less critical region of the flash. So that means you have to, if you want to remove, so three things I told. One is you have to find out what is the crack you are getting or you want, the formation is there. Then second is how it is creating. Then third one is how it is solving or how you have to solve. Right? So how you will solve it? You have to increase the flash thickness. If this is very thin, then you have to increase. And second is by relocating the flash to a less critical region. So somewhere you are finding, for example, what we talked about the hot softness. Similarly, you will find some like danger zone is there, or maybe some critical zone is there. So you have to little go far, or maybe you have to avoid that critical zone. It also may be avoided by hot trimming or stress relieving before the prior to cold trimming of the flash. And also sometimes how to remove that one. If you want to go for the trimming or maybe like removing or the cleaning or maybe the stress relieving. If you want to make it, probably it is easy to remove that, right? Is it clear?
So, yes, sir.
Then second one, another defect is there. And the another defect is known as the cold shot or the float. If you'll see the second part. Okay, so part B. So part one we have talked about already, and the second part you have the cold shot. Okay, you can see the schematic diagram. So another common surface defect is closed die forging is the cold shot or the fold. So a cold shot is a discontinuity produced when two surfaces of metal fold against each other without welding completely. So that means if you have two metal sheet, like sometimes we have overlap. Like whenever we are like when if you see somewhere sometimes when we are printing the papers, so sometimes two paper will come out. Okay, so the moment you have, so similarly, whenever you are putting some metal piece also, so sometimes it will overlap two surfaces. Okay, so the moment you have overlap, that welding or maybe that joint is not making properly. In welding means you do not think that that welding, typical welding what we are making. Welding means the joining or the like for example, the sandwich method. If you remember in composites we talked about. So welding means the two metal surface is not fixed properly. Okay, it will overlap to each other, and this can happen when metal flows past part of the die cavity that has already been filled or that is only partly filled. So sometimes that cavity is already filled, but still some is going there because you do not need that one, but still this is passing over. Or only partly filled because the metal failed to fill in due to the sharp corner, excessive chilling or high friction. So that means some of the parameter you are getting here. That means excessive chilling is there, or maybe the corner is very sharp, so again it is passing, or maybe some high friction is there, so that again it is trying to go inside. Then only it is. A common cause of the cold shot is too small a die radius. So that means if your die radius is too small, probably you have to see because this is a generalized statement. If this is too small, but that depends upon your like how much thick of material you are passing, what kind of whether this is soft or hard material you are passing. That also depends. But in the common statement or in the generalized statement, you have to think that if your die radius is too small, you can find on one cold shot or maybe the fold also from the name onwards you can find out. Fold means it is overlapping, and the loose scale or the lubricant residue that accumulates in deep recesses of the diaphragm scale pockets and cause underfill. And if you remember one time we talked about in machining, I think, okay, the underfill. So if you have loose scale, or maybe for example, if some material you are putting, or maybe the like whenever you are doing something like the chip in machining, you remember that chip actually we are putting. If this is very loose, or you are accumulating there, or the process is accumulating there, and also one more is lubricant residue. Whatever the lubricant we are putting, and sometimes after finishing some operation, you will find some like slurry or maybe some waste kind of material. If that accumulate also, it will find you will find some like defect there, because all the material it will not pass in a proper. Incomplete descaling of the workpiece results in a force in scale on the finished part. So also whenever you are not cleaning or not removing properly, so that also it will make some impact, or it will some you will some find a crack somewhere, whether it will be on surface, because inside probably it will be much more difficult because it is only connected to the surface. So the moment you have you are finding some connect to the surface, then probably, because if let's say some chips are there on the surface, Okay, but whenever you are making forging, so that one you will find some overlap kind of structure on the surface. So similarly, this kind probably it is very difficult to understand in the surface how it looks like. But if you can imagine some chips you are putting on the surface, or it is remain on the surface, whether it is if it will remove that one, probably you will find some holes inside, right? Is it clear?
Yes, sir.
Yeah, fine. Then next one we have the other two photographs or the images you can see in the bottom. So these are known as the internal crack due to the secondary tensile stresses. Whenever you are using some forces or the stresses what you are creating, so do not think that only one force you are using. So at the same time also you are creating some secondary forces or the secondary tensile stresses. And the moment you are using or maybe you are creating some secondary forces or secondary stresses, then also it will impact somewhere. So the secondary tensile stress can develop during forcing and cracking can thus be produced. Okay, it will be automatic, the equipment is generating. We are not forcing by there, right? And the internal cracks can develop during the offsetting of a cylinder or the round as a result of the circumferential tensile stresses. How it can develop? It is developed during the offsetting of a cylinder, okay, or around as a result of the circumferential tensile stress, whatever the tensile stresses we have. Near that we can find. And the proper design of the dies, however, can minimize this type of cracking. So here actually this is the, many our students actually normally you are thinking of the designing. So that is important. So if you will do everything from the beginning, so then you will not find the internal crack there. Okay, maybe you can minimize that the creating of the internal crack. So you have to go from the beginning. So when students what they are doing, they are just doing the experiment or maybe doing some research. Then when they are finding the problem, then again they are going back to the design process. So this is my suggestion that whenever we are doing any kind of experiment, so we are thinking that which is possible. Probably it will be delayed because initially if we think all the parameter and you have to fix it properly from the beginning, then it will take time because maybe you cannot finish on time. But if you will go in a process or in a proper way, then whenever you will find some difficulty, you can catch it immediately. Because if you are doing something randomly, then finally you are getting because a lot of parameters are there. You cannot tell that only one or two parameters are there with us. So if you have a lot of parameters, then probably it will be much more difficult to find out where this problem or where we are finding or we are facing this issue actually. So initially you have to go for the proper design of the dies. However, you can minimize the internal. In order to minimize the plugging or the swelling during the offsetting and the development of the circumferential tensile stress, it is usual practice to use concave dies. Okay, so that means whenever you are thinking about the proper design, then also you can think about what kind of dies actually you will make. So I think we have talked about the two kind of dies initially when we talked about the concave and convex dies. So that also you have to. And the next we have the internal cracking is less prevalent in closed die forging because the lateral compressive stresses are developed by the reaction of the work with the die. Because for example, when we are talking about, we have the system, then we have the die and the also pons as well. So I will show maybe one kind of structure in powder metals, but we are making. So that reaction also it is possible because you are pressing something and that depends upon the die and that depends upon the force, that depends upon the velocity or the the speed, and also that depends on the points, right? Is it clear?
Yes, sir.
Yeah. So next one we have it's a new technique actually. So of course we have the
So,
turning. Yeah, yeah, please.
so what about using ultrasound or something they use to find these cracks?
That is we call the NDT, non-destructive testing. So we have a lot of variety of tests. I think you have covered that course or not yet?
So,
NDT.
we have not covered a course, but I just heard it here and there. It's quite common.
Yeah, not quite common. Normally, we are using the common is the penetrant testing. For you have a liquid dye. Okay, so if you have some cracks inside, if by visual testing, visual means only with the help of our eye, normally we are looking. But if it is a big one, you can use by visual, directly you can see. But if you have the small crack, so better, this is cheap because it depends upon the price also you have to go. A lot of tests are there. Probably, I think we have studied 8 or 9 tests. but you are taking the ultrasonic or something. But we are normally going the cheaper way, the dye penetrant. So, there is a liquid dye. So that dye will put on the surface. So maybe after some time you will see the color and the dye color, it is going inside. The moment it is going inside, you will find the crack. But others are there, but these are expensive. Okay, normally we are not preferring. But if you are going very small things or very expensive things, then probably because which is very sensitive. But when we are talking about the metal working, I do not think we are going there. We are only going up to the dye penetrant. Okay, but that also we have a
Okay,
course. I think we have variety of NDT tests are there. We have a separate lab also. But I checked, we have not so many of equipment. But in Chennai, I think we have a institute of what is this? I am a member of actually the ISMT, Indian Society of Non-Destructive Testing, ISMT Chennai. I forgot the address actually. They are giving, and these are very, how to say, very expensive courses are there, and they will give you, let's say, 15 days or 1 month. They will take big money. Maybe the admission fees, I think 7,000, 10,000, 20,000. You can do it, and your job guarantee is there, job security is there. But very like careful job you have to make it. Otherwise, this is fine. I also tried when I finished my master's. I think I was trying to do. I applied also in Chennai. I will study some extra courses, but maybe due to some other reason, I think I could not make it. But there are some courses and the good institute. I'm a member of that IS. If you want, then maybe we can discuss in other day. Okay, if you want to continue that.
okay, sir. Sure. Thank you.
Yeah, then next we have the powder metallurgy force. I think that also we have covered in composite because this is a new technique now. Of course, I have done a few experiment with the help of the powder metallurgy, and also now also I am making with the preparation of some alloy or high entropy alloy with the help of powder metallurgy. So this is a new technique, and you will not do, and you will not like do some bigger experiment. Okay, the equipment is very small, and also the equipment you need not so expensive. So a new and rapidly growing area. So that's why I mentioned here a new and rapidly growing area is the production of closed die forging from powder metallurgy platforms, or we call a PM force. That means powder metallurgy force. If you'll see the schematic diagram here, so two kind of schematic diagram I have prepared here. So one is in the first part, we have the uniaxial compaction. And second one, we have the double compaction. Uniaxial means one side is fixed and one side you are just giving the force or the pressure. You can see here the bottom punch, this is fixed here. Okay, but you are applying the force here on the top side, and your powder material is here. You have. Okay, and this is the die wall here, and this is the upper punch. But if you see the double compaction, so that means the two forces from the up and from the bottom you are applying. Okay, so normally when I was doing actually from the two side, because the small setup actually we have, so we call this as hydraulic press. So you can put the this die, you have to prepare by yourself. Yourself means you have to give to some company whether the die, let's say this die diameter is, let's say if you need a 10 millimeter or maybe 20 millimeter, this depends upon. And sometimes also many people they are working, because I saw some of my colleagues actually earlier they were preparing 2 millimeter die or 3 millimeter die, like very a small kind of small shape you will get there. But it is very difficult to control whenever you will remove that tablet, for example, from the shape. It is very difficult because by your hand it is very difficult to keep. Maybe sometimes it will break. But if you take little bigger, let's say 10 millimeter or maybe 8 millimeter or 12, 15 millimeter, probably you can at least keep it. Okay. So the use of sintered PM performance, sintered rather than the bar stock as a workpiece offer advantages of improved material utilization. Okay, so why actually we are going for the new technique, or why we are going for the rapidly growing technique, where many researchers they are using this powder metallurgy technique. The use of the sintered powder metallurgy or the powder reforms rather than the bar stock, because whatever we have discussed up to now, we are using a metal piece, we are using a bar there, right? So as the workpiece offers advantages of improved the material utilization, because here we are using the powder only. Okay, so improve the material utilization through reduction or elimination of machining, forming to final size in one forging stroke, uniformity of structure, and a reduced directionality of properties related to conventional forging. So that means whenever why we are going for the new technique, because we have little limitations there, or maybe some limitations there. To overcome that limitation, we are going to the new technique. Okay, of course, we cannot tell that all the limitations of whatever we have in the previous technique, we are removing everything. whenever we are removing some portion or some limitations, we are going to the new technique. Of course, in that new technique also we will find some limitations. Okay, so that's why we are going for to change some technology there. Of course, in the beginning, we have to think about the cost, because many times the students, they are asking about, when we are going for the new technique, this is costly. Of course, it will be costly. But initially, when you are changing some technology, you have to go for the costly one. Maybe when people, they will follow the same technique, then the cost drastically it will decrease. So here, part of the benefit we are getting, we are benefit the utilization, the improved material utilization. We are going for the elimination of the machining, because whenever we are going for the machining, that machining will be, it will take a lot of time, and the equipment is expensive. Then you need a bigger space. Okay, because here you need a small space. Forming to final shape in one forging stroke. Okay, for example, if you want to go for maybe 10 kilonewton or 20 kilonewton, in one stroke you can make it. Okay, and third one is the uniformity of the structure, because this is powder. Okay, so if you want to press it, you will find some uniformity. For example, if you make it a tablet like 10 millimeter into 5 width, or maybe the height, also you can make it. And reduce the directionality of the property. Also, for example, what kind of property you need, because here you will find some porosity, right? Because this is at the powders, so you will find some porosity there. And of course, you have to find out how much of porosity is initially there in the powder. Then after forging, what should be the reduce of the porosity. And working with the sintered powders metal preform induces the new aspect to the mechanics of metallurgy of plastic deformation. So if you want to go for in a different perspective or new technology, of course you have to find out the different mechanics of that mechanism. So because it contains a dispersion of interconnected voids, the deformation of powder metallurgy preform is much different from a conventional fully dense organism. Because here we have voids, so that means here it has a lot of pores there, or the porosity, high porosity material. Wherever, whatever we have discussed up to now, these are the dense material, because this is totally the material you are forcing, right? So these are both the mechanisms will be different. And with the powder metallurgy preform, the workpiece decreases in volume during plastic deformation. The porosity is closed off and eliminated by the act of plastic deformation. With the help of the plastic deformation, initially the volume will be high, okay, and finally the volume will be, because you have to press it. The moment you have to press it, so the volume will be decreased. But whereas that we have discussed up to now, so the initial volume is equal to the final volume. That way we have calculated. But here the initial volume, whatever you have, because initially you have lot of force are there. The moment you will use the plastic deformation or the mechanical working with the help of the powder metallurgy, your volume will drastically decrease. Then we will use the powder metallurgy. Right? Is it clear? Yeah.
Yes, sir.
Yes.
So the presence of void. So now when you have void, do you know how to calculate the pore size? Any new technique you have? Any idea? Maybe I told several times in composite material. Who has attended the composite material can tell. Anyone? I remember. One is the general term whenever we are talking about the density. In that way, we will calculate, because that force, I think, in composite we have calculated. You remember that one we talked.
Yes, sir.
Yeah. But other also there is a BET analysis, BET. Okay, so that also I do not know. Here I think probably in Chennai, I do not know. In Vellore we have that that equipment, BET analysis. So you will put your sample. There is a glass. Like small cylinder or maybe bigger kind of structure. So we'll put your sample maybe around 5 gram, or maybe 5 to 10 gram you will put. Then maybe after 1 or 2 hours, if you will set there, then you will find the porosity of that powder sample. Okay, so these are the new technique actually we have nowadays. So it is better. You do not need to calculate every time. We have a lot of equations. So instead of that equation, if you will calculate manually, probably you will find somewhere wrong. Then also it will be not popular nowadays, because earlier it was popular. But now if the same sample you will put that equipment and you will tell that I have used the BET analysis, maybe many people they will tell yes, this is a new technique and advanced, right? And the presence of voids causes significant decrease in local ductility, which increases the likelihood of fracture during the forcing. Okay, so when we are talking about the metal working, also you have to think about the fracture. If this fracture is happen, then also you have to think whether this is you use or you do not use that one, because all the property what we are talking. However, the forming limit concept can be applied to the design of powder metal electrodes to prevent the fracturing of force. That also like one known as the forming limit concept. That one we will talk about in sheet metal form. Okay, so that one. So I just mentioned here a useful technique for the controlling the failure. So if you do not want that failure also, you have to check. If you will control, because everything you have to control. If you cannot control, then it will fail some. So all the parameter you have to think, because sometimes we are doing the any heat treatment in case of vacuum. Okay, so some people they are telling that sir, vacuum, if we'll make it, it will be good. But the moment you will make it a vacuum, so if the inside volume, because some waste gas or the maybe whatever the volatile impurities, it will go out. But how will go out? Because there is no space to go out. Okay, so that means it will accumulate, and the moment it will accumulate, then high pressure will create there, or you will find some more pressure inside. So maybe it can happen something more. So you have to find some inlet there. So that's why we are recommending every time you have to put some argon atmosphere. If the moment you will put argon atmosphere, so that means inside instead of vacuum, if you put argon, so that means the outside moisture cannot come inside. So the moment you are creating or the volatile impurities will coming out, that one also will go out with the argon outlet. Okay, so here also we are talking about the forming limit concept. So that means you have to control the failure, because the failure is a much more biggest factor here. But that one in detail we will talk about in sheet metal form. Okay, so there is a limit diagram, we will discuss that. And the presence of voids increase the surface area over which unfavorable oxidation or the contamination reacts. So one is the moment you have voids or the pores inside, so there will be some reaction happens. For example, the oxidation reaction. Okay, so that's why what we are proposing normally, the powder, whenever you will prepare everything, if this is oxidized, maybe you cannot make it. So better to go for one inert atmosphere area. So you can prepare all the powder sample there. So basically we are going to the globe box. Globe box is a big chamber. That inert gas is there inside argon. So you have two globes. Maybe it is very difficult to maybe explain you, because you do not know. Maybe have you heard about desiccator? Desiccator, where you are keeping the sample, the
No, sir.
outside small desiccator. One second. Can you see my screen? Google.
PDF only, sir.
One second. Can you see the screen?
Yes, sir.
Yeah. So this is known
Yes,
as the
sir.
desiccator. So what happened, for example, inside you can keep your sample inside. So we can close the chamber, and there is a glue here, in the middle. So that means the upper chamber you can just close here. So this is for the I'm not telling this is totally safe, but still you can keep your sample there. Okay, but for the long time if you will keep, I think this is not correct. But if you will go to the box, this one. Okay, so if you will do the globe box, this is normally easier. And this is the good one. And of course, the equipment is expensive. And can you see the photo? Here you can see. So inside is the argon atmosphere. It's a big box. Inside is the argon atmosphere. I think this one is better. You can see. This inside is the argon atmosphere. You have two globes are there. Okay, and this is the vacuum chamber here, and this is the door actually. This is the entrance. So you can put your sample. If this is a big sample, then you can use this big box. You can put there. And if you have a small sample, you can put in this small sample. Okay, and you have a motor here, and if you want to take vacuum of this small chamber, so then you can use this motor, and there is a screen and there is a monitor here. So in this, within this monitor, you can find out how much of hydrogen, how much of moisture and how much of hydrogen, how much of hydrogen and how much of moisture is there inside. If you need in ppm or ppb, so it will control, because it will, for example, if you are putting some water sample here, so that means here the moisture and hydrogen will show that fluctuating, or it will increase. The moment it will increase, then you can stop your work. Then automatically it has some inside some filters are there. So this filter will absorb to your original position less than 0.001 ppm or 0.001 ppm. Okay, then again you can work. Right, these are normally we are calling globe box. These are expensive, maybe around in Indian rupee 7-8 lakhs, but this is recommended. I think in chemistry department we have one globe box. Okay, maybe when you have free time, maybe when we will meet, probably we can see this kind of gloves. Fine.
So where are the gloves for the smaller cylinder that you showed?
Where are the?
So the gloves are only for the large box. So how to access the sealed smaller cylinder which you mentioned?
This one, this small one.
Yes, sir.
No, this is for the entrance. In this way, you can put your sample, and your sample you will keep here inside. Okay, because
Okay,
there are two
okay, sir.
gauges here. So what we will do, let's say initially it is vacuum position, that's a small one. Only the big and small difference is you can put the bigger sample here and you can put the smaller sample here. So what you will do initially, what you will do, initially this small chamber is in vacuum position. Okay, so you can remove the vacuum here. Okay, then you can open the door, you can put the sample inside, you can close the door here. Okay, you can close the door. The moment you will close the door, then you can take the vacuum, this chamber. Maybe 3 times you can make, or maybe 5 times. Normally it is recommended 3 times. The moment you will take the vacuum, so that means inside there will be no outside noise. Then inside there is a door, another door inside. You know the big box and the small box here in the center. Another door is there. So the moment you have removed your vacuum here, then that means inside there is no noise. Then you can open the inside door. The moment you will open the inside door, then take the sample from here to here. You can use this glove box. You can put your hand like this. Here you can see how it is
Okay, so
putting.
understood. So it's like an airlock. So first you take the
Yeah, yeah,
vacuum
yeah,
and
yeah, 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 yeah. Okay, so this is normally expensive, but normally I use this one. For me, I feel this is the safest one. Okay, instead of that desiccator. Desiccator is if immediately you are putting there, but inside, for example, the moment you will open the upper lid, then the moisture can go inside. You cannot, there is no option. But in some desiccator, what you will do, some desiccator, if you will put a vacuum pump there, you will make a hole, then you will connect the vacuum pump, then you can make it. That also possible. You can make it. And that depends upon. Okay. Yeah. Fine. I will do that. Okay. Yeah. So the presence of voids increase the surface area, and also whenever you have a lot of pores there, so there is a possibility of to make this powder oxidize. Then also some contamination also it can happen because you have some pores. So if some contamination will go inside with the help of that pores, then also you will not find in a proper way. So that is this recommend that all the parameters you have to think properly. The basic plasticity mechanics of a porous powder metallurgy preform can be described by the following relation. The relationship between the densification and the plastic deformation, because you have to think about the densification. That means initially it has pore, the volume was big, and finally when you are making it dense, for example, when you are pressing, then you will find a dense material. Okay, or maybe the tablet what you are getting. And the plastic deformation is achieved through the relating the Poisson's ratio to the fraction of theoretical density. Okay, so this is the equation, the Poisson ratio equal to 0.5 into the actual density divided by the theoretical density square. This is normally equation. You have to go to that equation when we are talking about the mechanics, right? So this relationship hold for a hot and cold working provided the preform has been sintered, and the classical theory of the plasticity is based on the assumption of the, some assumptions again you have to think about when we talked in the last module, I think the hydrostatic component and the von Mises yield criteria. Also here also you can make it, or you can go in a similar way also whenever you are talking about the mechanics of the powder metallurgy. So here one scientist, Kuhn, he has shown the yield criteria when they have talked about. So the sigma 0 equal to this equation he found, and where we have talked about these two equations actually. Okay, so in the beginning, actually, if you remember our von Mises criteria, so the first term is known as the basically known as the von Mises criteria we have talked, and the second term is account the porosity. So the Poisson's ratio, what we have discussed in the last. So two terms you have to go, because in the initially when we are talking about the only the plate, we are talking about only the yield criteria. When we are talking, we are finding only, or we are going through the von Mises criteria. But when we are talking about the powder metallurgy, here two things are important. One is the von Mises criteria, and second we have the porosity. Okay, both the things you have to think, or you have to consider. Apart from this, also several other yield functions for compressible the powder metal materials have been proposed. Many researchers actually they are proposing whenever they are thinking if this is one criteria may be prepared by Kuhn. Based on this, maybe some people they are also thinking about other, because that is research when we are talking. Okay, so maybe you have, maybe if you are interested about the powder metallurgy or maybe the mechanical working, of course, also you can think where some lacuna is there, or maybe where some research has not done. Probably you can think the parameter based on this parameter, again, you can improve it. Okay. Yeah. So then it is the last part of this presentation, the residual stresses in forging. Of course, we have talked maybe in the beginning also, I think somebody was asking about how to remove the residual stresses in the beginning when we talked about the heat treatment, many things we have to. But now in forging also, okay, in the similar way, but in the forging also, how the residual stresses in forging actually we are finding. So the residual stresses produced in forging as a result of inhomogeneous deformation are generally small because the deformation is usually carried out well into the hot working region. So if you think about the I told about the somewhere the material you are finding the brittle. Okay, so that red hotness, if you remember that word I was using. So here also sometimes we are not finding homogeneous everywhere. The moment you are not finding homogeneous, then it will be difficult. That's why I recommended sometimes when we are making the heat treatment, you have to increase the temperature up to certain limit or up to certain temperature with a certain rate. Then you have to hold it. While you are holding it, if you want to hold it maybe 1 hour or 2 hours, then maybe if this is not homogeneous, probably it will be homogeneous in that period. Then again, you will find this is the accurate one, and after that you do not need, then you can go for the cooling at a certain rate. However, the appreciable residual stresses and the wrapping can occur on the quenching of steel forging in heat treatment. One more thing also, maybe is every time I'm suggesting that one, the moment you are quenching, because that quenching media is also you have different. One is furnace quenching, then oil quenching, then water quenching, then also the immediate, for example, sometimes we are the room temperature quenching. Automatically it is quenching, but sometimes we are putting in the oil bath immediately or in the water bath. So that also depends. Special precautions must be observed during cooling of the large steel forging from the hot working temperature. Of course, if you have a different kind of material, if you have steel piece or if you have the copper sheet or maybe any non-ferrous sheet, also that temperature or that parameter is different from each other. Large forgings are subject to the formation of small cracks or flakes at the center of the cross section. In large forging, of course, when we are talking about the accurate things in laboratory scale, it is very difficult when we are talking about the mechanical working. I told in the introduction part, of course, you have to go for the large scale, but also if you are thinking about, because in one way, if you are thinking good, maybe you are finding again some difficulty or even some limitation there. So what are the limitations? The large forging are subjected to the formation of small cracks or the flakes you are getting there. And the flaking is associated with the high hydrogen content, usually present in steel ingots. Large size coupled with the presence of residual stresses. Of course, if you have the flaking, also it relates to the composition. For example, the hydrogen or with the moisture or with the oxygen is there. That also depends because it will accumulate there. And the moment it will accumulate, then you are finding some defects there. Okay, or maybe the residual stresses there. And the last, in order to guard against the development of high thermal or transformation residual stresses, large forgings are very slowly, okay, from the working temperature. So if you will see the, the blacksmith where they are forging or they are hammering. So initially what they are doing, increasing the temperature, but they do not have any parameter. They are just doing manual. They do not have any automated setup. They are just doing, and also we are buying that because we are thinking this is the cheap one. In the lower price, you can buy it. But if you want to go to any automated shop, probably it will be expensive, right? And this may be accomplished by pouring the forging in ashes for a period of several weeks or in the controlled cooling treatment, which is used for hot roll, railroad rail and the certain forcing. So some process also they have. If you can take some any kind of example how, or maybe you can just think of one kind of ferrous material, let's say, how you will find this defect, what are the causes and what are the type of causes you are getting, then how you can remove it. For example, here they are making controlled cooling treatment. If the cooling treatment or the whenever after heat treatment you are cooling it, you have to control it. You cannot tell that this automatically we are cooling. Okay, so you have to control it. How you will control it? With the cooling rate, let's say 2 degrees C per minute or 10 degrees C per minute. Whether you are cooling very slowly or maybe rapid cooling, that depends upon you. Okay, and you means it depends upon material. But how you are doing, because there is no other people, we have to do. Okay, and also you have to think about the cooling cycle, which bring the forging to a safe temperature in number of hours. sometimes we do not have patience. So every time I'm telling that you should have patience. Do not think that maybe within 1 hour I will finish it, then I will just go. You have to think very carefully because this depends upon the like, otherwise if you are not thinking properly, then the company will lose many things because the customer demand product. Let's say if you cannot prepare, then like, this is waste of money. And the use of vacuum degas seal largely eliminates problem with flake. Okay, so one is the vacuum furnace also what we are talking about. Sometimes, uh, two kinds of thing. You can do one thing maybe when you have free time, when you will come back, maybe we can do also together. Some sample you can take any ferrous or non-ferrous sample. You can hit it with a like, the normal furnace, and also sometimes you can take for the better comparison, we can take a vacuum furnace or maybe the argon gas furnace. So you'll find the difference. Or maybe I'm not telling that the composition you will find different or something. Maybe the time also you can save. Somewhere you will find different. Okay, so these are all about the residual stresses. Okay, if you have any question, you can ask. Yeah, any question?